Hello. Yeah, very good evening, everyone. Am I audible?
Good evening, sir.
Good evening, sir.
Good evening, sir.
Good evening, sir.
Very good evening. Okay, perfect. So in today's class, we will discuss questions on potential and potential energy. Okay, so I hope those topics are covered in your regular classes for everyone. Yes. Okay. All right. So let's get started. I'll just share my screen. Yeah. One second. This. Okay. Actually, let's take this one. Just a second. Huh? Yeah. Okay. So let's start with this one. Okay, so let us see how we can solve this. Right. So here we are given that the potential in a certain region, okay, is given by this expression. Right. We can see that the potential only depends on the x coordinate. All right. A and B are some constants, and we want to find the distribution of the charge in this particular region. All right. Okay. So first, what I'll do is I'll find out the electric field. Okay. Since potential only depends on x, the electric field only has the x component, right? Which we can find by this thing. All right. So that gives us okay. So the electric field, the total field is only this much. All right. Okay. Now, in this region, we will pick a small volume like this. Okay, let us say this end is located at x equal to x, and this end is located at x equal to x plus dx. Right, so it's a tiny portion with thickness dx. And let us say that this area on either side is A. All right, okay, so the field on both the sides, right, over here it is going to be, let us say, some value E, and over here it is some value E plus dE. All right, we know that it's in the x direction. Okay, so now we can think about the flux through this surface or through this closed surface. Right. So the closed surface, by that I mean it's a, it's a cuboid with very small thickness like that. Okay, so think of it like that. All right. So the flux exiting from the surface is E plus dE into A, and the flux entering is E into A. Right. So this will be the net flux through this closed surface, right? And that, according to the Gauss's law, should be equal to the net charge inside into divided by epsilon naught, right? So let us say that at this particular location, the charge density is rho, right? So we can write this as rho into the volume, which will be equal to A into dx divided by epsilon naught. All right. So this is equal to then dE into A is equals to rho A dx by epsilon naught. All right. Okay. So we will lose A from both sides, and we can say that from this rho is equals to epsilon naught into dE by dx. Okay. We already have electric field, so we can differentiate it again. So that gives us 6A epsilon naught into x. Okay, and that's the final answer, right? So the volume charge density basically increases linearly with x. That's what we're trying to say here. All right, okay. Questions here? Okay, so let's move on to the next one. Try this one. Okay, so let us see how we can solve this. Here we are given a thin disk, okay, and we have a uniform surface charge density on it, right? And we want to find the potential because of this disk, okay, at a point which is on the edge of the disk. All right, so the situation is something like this. This is disk, okay, and let us say this is the center of the disk, okay, and we want to find the potential at, let's say, this point P over here. All right, okay. So to do that, clearly we have to divide the disk, okay, into a bunch of elements, right? So we can find the potential because of each element and then integrate it, right? So the kind of element that does work in this case, okay, is a ring element, something like this. Okay, so we will consider a ring element like that. Okay, the center of this ring is P itself, and let us say that the radius for this particular element is R, and this angle theta over here. All right, this ring element, say, has a thickness of dr. Right. So we will consider that the disk is made up of, a bunch of such ring elements.
So
Right.
I didn't get how are you considering that ring?
How are you in the sense?
So how took the particle like that in the ring? It's a disk, right? Thin disk.
Aha. Yes, yes, it's a disk. So I'm assuming
So the
that
ring has to be on the surface of the disk.
yes, true. Okay, the disk has a very small thickness though, right? Okay, so this ring that I have assumed, okay, it's an element, right? Okay, whose thickness whose thickness in the diagram is dr, right? And obviously it will have the same thickness as the thickness of the disk, right? That thickness is normal to the plane of the diagram. That's what I'm trying to say, right? So that is how we are considering. Clear on this, Rahul?
Yes.
So I had a doubt.
Yes.
So I'd done something similar, but instead of taking a ring, I'd taken like a rectangular strip. Would that work instead of the ring?
Okay, if you take a rectangular strip, yeah, that could work. But how are the calculations coming
Yes,
along
yes.
when
So
you
they
try
actually,
to?
yeah, they were a little difficult because it was an
Mhm.
equidistant. So I had a
Yeah,
variable
yeah.
distance.
It's a variable distance, right?
Yes,
So the calculation might get very tricky. But in principle, I mean, yeah, you can divide the disk any way you want. Okay, and
yes.
basically you have to set up the integration. Right. It just so happens that with this, the integration is sort of easy. Sort of easy. It's not very easy, but sort of easy. You'll see that.
So and there's no overlap between two consecutive rings.
There is no
Overlap between two consecutive rings.
no, there is no overlap between two consecutive rings, right?
All
Like
right.
the next
Yes.
ring over here is gonna look like this, basically.
All right. Thank you, sir.
Okay, so let us say that the charge on this ring is dq. Okay, and hence we can say that the potential because of this at point P will be equal to k into dq by r. All
So
right. Okay.
how are the rings oriented? I mean, are they in the same plane as the disk?
Yes, yes. We are assuming that the disk is a collection of such ring elements. These are not full rings, right? These are not entire
Oh,
rings. These are portion of rings, right?
okay.
So we are assuming that the disk is a collection of such ring portions. All right. Okay. So right. So now we want to find out what is dq, right? So for that, we'll say that we need to find what is the area of the ring for this, or area of the ring portion, I'll call it. Okay, it's not the entire ring. So for the ring portion, we can say that its area is equal to the length, which is equal to r into 2 theta, right? We can say that if that's theta, then this is also theta, right? So r into 2 theta, that is the length, and its thickness, we are calling it dr. So that's the area. Okay, and hence the charge dq will be sigma into dA. Right, so let's put that in the potential. So we'll have K into sigma into R into 2 theta into dr divided by R. So we use the R and gives us a d as 2k sigma theta into dr. All right. Now you can see that when we change the ring portion, okay, both small r and theta are going to change, right? So we need to come up with a way to relate these two. Okay, and the way to do that is something like this. Okay, if I consider this point as, let us say, point X, okay, and this point as point Y here, right? So Py is clearly a diameter, okay, and if I join point X and Y, we know that this angle is going to be 90, right? So we have PXY is a right angle triangle. Okay, and since it's a right angle triangle, we can say that small r is equal to 2r, which is the diameter, into cos theta. All right, so from this, I can say that dr will be equal to minus 2r sine theta d theta. Okay, which then we can put in the above equation. So this will be 2k sigma into theta, and dr is minus 2r sine theta d theta. All right, so upon simplifying, this is minus 4k sigma r theta sine theta d theta. Okay, and then we can integrate this to find the total potential. Okay, now what will be the limit of integration? Well, you can see that the first element, the first ring portion, if we consider, right, that will be somewhere something like this, right? It will be, I'm just exaggerating it, but it's going to be a very small portion like that. Okay, and for this portion, theta is practically going to be 0. Okay, and the last portion is going to be very close to point P itself, right? For which the theta will be close to 90 degrees. Okay, we can understand that as the ring elements get closer to point P, the value of theta will continuously increase, right? So the integration is from 0 to pi by 2. Okay, you have to use the product rule for integration, right? You can see that because you have theta and sine theta both. Okay, so that's just the math part. Okay, after we do this, we'll get the final answer, right? So I'll just tell you what the final answer is. It's there we go. Sigma r by pi epsilon naught. Sigma r by pi epsilon naught. Right, so that is what we will get at the end. All right, okay, doubts here?
So for the same question, can we take like a bunch of rings from the center and then when we integrate find equation and find its potential at R?
Okay,
From
you mean to say a complete ring
yeah, from the
with
center.
C as the center?
Yeah, and like we keep expanding and all.
But okay, no, see, the problem with that will be, Avnish, if you take a ring, okay, then say you pick one particular ring. Okay,
Yeah.
now for different points on the ring, point P is at different distances.
Oh.
Right.
Yes.
So we'll not have an expression for dV itself.
Yes. Yes.
Okay, so that's there, right? So in my understanding, okay, the most important thing over here is to pick the kind of element that we have taken, right? Which is the portion of a ring. Okay, this is something that we do not see very often, but this is something that works best in this situation, right? So that is
Yes.
something that we need to learn. Okay, and the second is that, PXY is going to be a right angle triangle. So we can write a small r in terms of capital R.
Yes. Thank you.
Right? Okay. Yeah. Any other questions here?
Sir, how do we know that each point on the small ring is equidistant from Y?
It's
Oh,
not.
sorry, sir. Sorry, sir. I
Ah,
saw something else.
yeah. Okay. Sure. Fine. So now let us move on to the next one. Okay, so this is a very important derivation also. Okay, and I think it will help to remember the final answer for potential. Okay, I have seen some questions, right, where you have to start with this equation and then take it forward. All right. Now let's try this one. Okay, let us see how we can solve this. So here we are given a solid sphere, okay, which is uniformly charged. And this solid sphere has a cavity of radius 1 centimeter. Right. We want to find out what is the potential because of this solid sphere at a point 4, comma 0. Okay. Now see that the radius of the sphere is 5 centimeter. Okay, meaning that point P is inside of the solid sphere. All right. Okay, so that is the first thing we notice here. Okay. Now, in your regular classes, you would have studied that if I have a solid sphere, which is uniformly charged, okay, and if there is a point P, let us say at a distance of r from the center, okay, and if I want to find the potential at this point P, okay, then the expression for that is this one, kq by r, capital R being the radius, plus kq by 2r cubed into r squared minus r squared. Okay, that is the first thing. All right. Now, what we have here is that we have the similar sphere, okay, but it has a cavity. Okay, so let us see how we can solve that one. Right. So let us say that this is the similar sphere, the cavity. Okay, so the cavity is somewhere over here. And we are told that the center of the cavity is at 0, 3. Okay, and point P is over here at 4, 0. Right. So now we can say that the potential at P, okay, or let me put it this way. Okay, potential at P due to full sphere. When I say full sphere, I mean without cavity. Is equal to potential at P because of cavity plus potential at P due to rest of the sphere. Right. So this is what we want to find out. Okay. Now, this term over here, this we will find out using equation 1. All right. You can see that we are given everything in that equation. Okay. So this we can find out. Right. Now, in order to find out the potential due to cavity, okay, that's easy enough because point P is outside of that cavity charge. Okay, so we can consider the cavity to be a point charge. Okay, so to be specific, we can say that Vp of cavity would be equal to K into Q, right? Q will be the charge of the cavity. Okay, divided by the distance between the 2 points, right? So you can see this is 3 and this is 4. So distance is going to be 5 centimeters. So 5 into 10 raised to minus 2. All right. Okay. Q we can find out as because we are given the density. Okay, into 4 by 3 pi and the radius of the cavity, right, which is 1 centimeter. Okay, so my point is basically all these numbers are given to us, so we can find VP cavity also, right? So that is how we can solve for VP of rest of the sphere. All right. Okay. Questions here? All right. So when we do this, for your reference, the final answer turns out to be 30 point, 35 point something volts. 35. Yes. Okay, that's the answer. All right. So now let's move on to the next one. Okay, let's try this.
So I had a doubt checking the second part of the question.
Yes, Ashok, tell me.
So can I do it using integration? But it seems very complicated. I was trying to integrate with respect to x or the
Mhm.
displacement from the mean position, but it seemed quite complicated.
Right. Actually, we can use the concept of potential here.
Oh, okay. So I'll try it.
Okay. So let us see how we can solve this. Right. So here we are given a ring. It has a charge capital Q. We are given a hollow sphere. It also has a charge capital Q. Okay. And there is a negative charge of small q is placed at the midpoint. Right. Uh, so we want to find out, first question is, that when we release this minus q from point B, right, towards which side it is going to move, right? That's the first question. And second is, with what velocity, it will reach the, either shell or the ring. All right. Okay. So let us see that. Right. So uh, let's try and find out what is the resultant electric field at point B. Okay, so we can see that because of the ring, we know that the expression for the field is k into q into x divided by x squared plus r squared raised to 3 by 2. Okay, and the value of x over here is 2r, right? And for the hollow sphere, the equation is simply we are outside the hollow sphere, so that's just kq by 2r whole squared. All right. Okay. So if we compare the magnitude of these two electric fields, okay, it turns out that the field of the hollow sphere is stronger. Okay, E2 is greater than E1. Okay, and hence the attractive force because of the shell is going to be larger. So the point charge will start moving towards the shell. All right, so that's the first part. Okay, now in the second part, we want to find with what velocity it will reach the shell, right? So clearly we want to find out, okay, what will be the velocity of this point charge at this point, let's say point P over here. All right. Okay. So for that, we can use the idea for conservation of energy. Right. We know that electrical force is conservative in nature. Right. So the total energy of the system will be conserved. All right. So at point B, right, what is the energy we can say at B? Okay. It will be equal to the charge Q into VB. Okay, and it will be negative because Q itself is negative, right? And the VB is the total potential because of the shell and because of the ring, right? So in terms of an expression, the potential of a ring, we can find out, okay, like this. So if I call this distance as R, okay, R we can easily find out. Okay, then it is going to be KQ by R. So because of the ring, it is KQ by R, and because of the shell, it is KQ by 2R. So that's the energy, potential energy at point P. Okay, clearly at this point, the point charge is stationary, so its kinetic energy is 0. Okay, at point P now, we can say potential energy is going to be negative Q into VP, right? So this now we can write as Q, and let us say this distance is R dash. Okay, that also we can find out. So KQ by R dash plus KQ by R. All right, and kb will be some value, right? Half mv squared. Okay, and now we'll say that the total energy at point B will be equal to total energy at P. All right. Okay. So UB plus KB is equal to UP plus KP. Right. And there is only one unknown in this, okay, which will be the uh, kinetic energy at point P. Okay. So we can find that. And from that, we can find the speed. All right. Okay. Fine. Questions here?
So can you show the answer once?
Yes. Answer, unfortunately, is incorrect for this question. So, yeah, it's given, but I was just going to tell you because they have made a calculation mistake. So do not rely on these answers, unfortunately, incorrect. All right. Okay. Yeah. Okay. So let's move on to the next one.
So 1 second, could you scroll up to the
Yeah.
please?
Sure.
Also, in the potential energy for P, is it not KQ by R by 4, the radius of the spherical shell?
Oh, I forgot. The radius is r by 4 here, right? Okay, okay, okay. True, true. So we have to use that at both the places then. Here also. Oh, sorry. No, this is fine only. We are outside, so this is fine only. But here, yes, it will be r by 4. Yes, that's a good observation. True.
So here the charge on the axis of the ring, right?
Charges on the axis of the ring. Yes. All right. Okay. So let's move on to the next one. Okay, let's try this one. Okay, let us see how we can solve this. Here we are given two positive charges, okay, out of which this capital Q is fixed here. And in the beginning, small q is at a very large distance. Okay, this distance over here we are given as d, right? And the distance a to c is practically infinite. All right, okay. So from that infinite distance, small q is projected with a velocity u parallel to the direction a to c. Right. We want to find out that in the subsequent motion, what will be the closest that small q will get to the capital Q. All right. Okay. Now, since both the charges are positive, we can say that the trajectory for small q would look, sort of something like this. All right. Okay. And let us say that at this point P, small q is closest to point A. Right? And let us say that closest distance is equal to x. Okay. Let us say that the velocity of small q at point P is equal to v. All right. So one thing we can say right off the bat is since point P is closest to point A, right? The velocity of small q at this point has to be perpendicular to the line OP. Right, because basically we are trying to say here is that small q is not going to get any closer to the capital Q, right? So that will only happen when the velocity becomes normal. Okay, so that is one thing. All right, so now we can say that throughout the motion of small q, the angular momentum will be conserved about point A, right? So angular momentum is conserved about point A. Right, so the initial angular momentum was mu into d, and at point P, it is equal to m into v into x. All right, so we lose the m from both sides, and we can say that ud is equals to vx. That's equation 1. Okay, second is the force is conservative, so the total energy will be conserved as well. Okay, so we can say that at this point, let us say call this as point see D here. Okay, so at point D, we have some kinetic energy, which is half mu squared. Okay, and the potential energy at this point is going to be 0. Okay, similarly at point P, the kinetic energy is equal to half mv squared. Okay, and the potential energy is equal to k capital Q small q by x. All right, so let's put things together. So we have half mu squared is equal to half mv squared plus kqq by x. Right, now we want to find x, so we can eliminate v using equation 1. Right, so for this term over here, we can say this is ud by x squared and qq by x. All right, so we can see that in this expression, x is the only unknown, right? We will get a quadratic equation in x, right? So we can solve for it. Okay, information wise, we are also given an information that d is root 2 minus 1. Okay, and from this we can say that k capital Q small q is equal to mu squared d. Right, so we can use these two in our calculations to find the x value. Okay, so after everything is said and done, the final answer is 1 meter. All right. Okay. Question? Yeah.
Sir, in this question, the the point Q is fixed, right? So
Yes.
somebody has to be applying a force on the charge Q to keep it from moving away from the other point.
True.
So then, that will be an external force and an external torque. So how can the things be conserved?
Okay. See, the external force part is true, but that external force is going to act at point A, right? So that force will not produce any torque about point A.
Yes.
Okay.
So what about energy conservation metric?
Right. See, the force is acting at point A. Okay, but A is fixed. So the displacement is zero.
Yes.
Right? And hence, no external work is being done on the system. Right?
Thanks.
Sure.
So it's true when you are neglecting gravity, right?
Yes. Gravity is neglected here. True. All right. Yeah. Any other questions here? Okay. So let's move on to the next one. Oh, okay. We are done with this. Okay. Now let's take questions from this. Yeah. Let's try this one. Okay. So here we are given two spheres, okay, out of which one sphere has a spherical cavity, right? And we want to find out what is the interaction energy of these two spheres. All right. Okay. So I can say that the interaction energy of these two spheres would be equal to interaction energy of the two spheres, okay, if both of them were whole. Okay, minus the interaction energy, okay, of A and the cavity. A and the cavity charge. All right, so that's what we can say. Okay, so let us find these two terms individually. Okay, let us say this is U1 and this is U2. Okay, so if Q is the charge on the spheres, A and B, okay, where B is without the cavity, so it's a whole sphere. All right, okay, then U1 is rather straightforward. It is K Q squared by R. Okay, that's U1. All right. Now let us try and find out what is U2. Okay, so for U2, we will consider this system. Okay, so this is sphere A. This is sphere B here. Okay, and the cavity is here. Okay, so let us say that small q is the charge on the cavity. Okay, this is the center of the cavity, C, and let us say this distance is C1, and this is the center of the sphere B. Okay, so here we need to use the distance between the two centers, right? So this distance, we can see that is going to be R minus R by 2. All right, so now from all this, we can say U2 will be equal to K into capital Q into small q divided by R minus R by 2. All right, okay, we can find out small q because we are given the density. Okay, so that's easy enough thing to do. Right, and then we just plug it over here, plug it in the original thing and find U. All right, okay, questions here?
So here we don't consider the interaction between C and C2, right?
No.
Is that because they're not like that's an internal energy between the of the whole sphere and not between those?
Yes, that will be the self energy part.
Yes, thank you.
All right, okay, good question. Yeah, any other questions here? Okay, so let's move on to the next one. Okay, this is about the field. So the field part you have already done, right? The dipole field questions. So I'll leave it. Okay, this is also a field question. If we have time, we'll come back to this. Okay, let's try this one.
Well, so for the second part of the question, are we just supposed to find potential at the origin?
No. Not at the origin, at the point P
Oh,
that is shown
oh,
in the
sorry.
diagram.
Yes, or greater than greater than. I thought lesser than lesser than. My bad.
Yeah. Okay. So let us see how we can solve this. So here we are given, an arrangement of four charges. Okay, two of them are positive, two of them are negatives, right? And in the first part, we want to find what is the potential energy of that system. Okay, Now that's an easy enough question. Okay, Q1 and Q2 are positive, and Q3 and Q4 are negative, right? So plus Q here, plus Q here, minus Q here, and minus Q here. Right, so it's a system of 4 charges. Okay, so the standard process, we will have total of 6 pairs over here. Right, we find the energy of each pair. Okay, and then add everything up. Right, so that's easy enough thing. Okay, I'll leave it to you guys. Okay, you can solve it. All right. Now for the second part, we want to find what is the potential. Okay, at a point which is very far away from this whole arrangement, right? So that's the part that we are interested in. Okay, so let's focus on that. Right, so what I will do is, I will find the potential at P, right? First, pick the 2 positive charges, then because of the 2 negative charges, okay, and then we can add it up. All right, okay, so because of the 2 positive charges, okay, let's see what we have. This is plus Q here, this is plus Q here, this is the center, and point P is here. Okay, this distance is R, this angle is theta, sorry, this distance is R, and this angle is theta. All right, okay, so let us join the charges with the point P. Okay, and let us drop perpendicular like this. All right, so if this angle is theta, okay, then we can say that this angle is going to be 90 minus theta, and this angle is going to be theta. All right, okay. Similarly, if this angle is theta, then this angle is going to be theta. Okay, which means this angle will be 90 minus theta, and this angle will also be theta. All right, so practically, we are saying here that the lines PA, PC, and PB, all 3 of them are practically parallel to each other. Okay, this is a good assumption because small r is very large compared to A. Right, so since we have parallel lines, okay, you can see that this geometry works out. Okay, all right. So now we can say that the potential at P, because of these 2 charges, you can write it like this now, Vp is equals to KQ. Okay, because of the top charge, the distance will be R minus this distance C to D, right? So that distance is A sine theta. Okay, and because of the other charge, the distance will be R plus this distance E to B, right? That is also equal to A sine theta. So that's the potential because of the 2 positive charges. Okay, now because of the 2 negative charges, we have a geometry like this. Okay, I'll follow the same process. This point is A, this point is B. Right. Once again, these lines PA, PC, and PB are practically parallel. So that's theta, that's theta, that's theta. Okay, and we'll drop the normals. Say this point is D here. This point is E here. Okay, so now we can say that potential at P would be equal to minus KQ. Okay, for the left charge, the distance is equal to R. Okay, now here this distance is A, right? So it will be R plus A cos theta. And because of the right charge, it will be minus KQ. And the distance is R minus A cos theta. All right. Okay. And then we can, just add the two potentials, right, to find the total. Right, so net VP is VP1 plus VP2. Okay, and that will be the answer. Well, we can do all the maths and do simplification and all if we want. Okay, take some terms will get cancelled out because R is much greater than A, right? So all of that will happen. Okay, so that's just the math part. Okay, you can do it. All right, so this is how we can solve this. Okay, questions here?
So what's the answer?
Sorry?
What's the answer?
Okay, answer is, 1 second, let me check. Okay, it's equal to, let me write it down here. Okay, it's equal to minus 2k q a squared cos 2 theta divided by r cubed. Okay, that's the answer. All right. Okay. Now, this is not a standard system per se. Okay. So the final expression is not, it's not something that is very useful for us. Okay. But nonetheless, this is the answer. All right. So let's move on to the next one. Let's just try this one. Okay. So it's a 4-part question. Okay. So take your time with that.
So should I answer all four in one message, or should I just do them individually?
You can send individually also. Sure,
All right.
no problem. Okay, so let us see how we can solve this. Right. So first, let us find the potential at R equals to R. Okay. So we can see that because of the outermost shell, it will be equal to K into 3Q by 3R. Because of the middle shell, it will be equal to K into minus because the charge is negative by 2R. Okay, and because of the innermost shell, it will be equal to KQ by R. Right? So that finally gives us KQ by R. Right. Then we can say at R equals to 3R. Right? So we are basically outside of the entire system. Okay, if we are outside the entire system, all these charges will behave like point charges. Okay, so I can just find the total of this, right, which is just going to be equal to 2Q. Right. So potential is then simply K Q minus 2Q plus 3Q, I can say, divided by 3R. So that's 2KQ by 3R. All right. So that's the first part. Okay. Now we want to find what is the field at 5 by 2R, right? So 5 by 2 is a point in between the two shells, right? So we're talking about a point over here. Okay. Now clearly at this point, there will not be any field because of this 3Q charge, right? The field will only be because of these two. Okay, and both of them will behave like point charges. Okay, so you can say that E at P will be equal to KQ by 5 by 2R whole squared. Okay, that is radially outwards, and K into 2Q divided by 5 by 2R whole squared. Right, minus because it's radially inwards. Okay, and then we can simplify it further if we wanted to. That's the second part. Okay, third part is important. We want to find the total potential energy of the system. Okay, which means it's a combination of self energy plus the interaction energy. All right. Okay. So that's, I think, is important here. Right. So let us do that. Okay. So this is U of self energy plus U2, which is interaction energy. All right. So first, if I find U1, okay, that will be equal to, for the innermost shell, it will be equal to KQ squared by 2R. For the middle shell, it will be equal to K minus 2q whole squared by 2 into 2r. And for the outermost shell, k into 3q squared by 2 into 3r. All right. Okay. Now let's look at the interaction energy. Okay. So for interaction, we have basically three pairs. Okay. There will be interaction between q and minus 2q, interaction between q and 3q, and finally interaction between minus 2q and 3q. Right. So we'll have three terms for that also. Okay. So between q and minus 2q, we can say will be equal to k into q into minus 2q divided by 2r. This is q and minus 2q. Then between q and 3q, it will be equal to this divided by 3r. Okay, and finally, between minus 2q and 3q, it will be this. Okay, and then obviously we can add these two to find the total. All right, okay. Make sure you understand the terms of interaction energy well. Okay, that's the only trick part in this question. All right, okay. So anybody has any questions on how did I write the terms for U2? Okay, great. So now let us look at the fourth part. Right. So in the fourth part, we are told that the innermost shell is connected to the outermost shell by a conducting wire. Okay. And we want to find out what will be the final charges, okay, on those two spheres. All right. Okay. So we know that when we connect these two by a conducting wire, okay, the potential of those two will become equal. Okay. So let us say that after connecting, the innermost shell has a charge Q1 and the outermost shell has a charge Q2, right? So right off the bat, we can say that Q1 plus Q2 has to be equal to 4Q. Okay. Q1 plus Q2 is equal to 4Q. Okay. Now the potential for innermost shell now we can write the potential as KQ1 by R and minus K into 2Q by 2R and K into 3Q by 3R. Right. Similarly, for the outermost shell, we can say potential will be equal to KQ1 by 3R minus K 2Q by 3R and plus K Q2 by 3R. Right, so this is V1 and V2. Okay, and then we can equate these two. Right, so that will give us another equation in Q1 and Q2. Right, coupled with this equation over here, we can solve for Q1 and Q2. Okay, so when we do that, I'll tell you final answer so you can cross check. So it's equal to 2 by 2 and 7Q by 2. All right, that's what we'll get.
So I had a doubt regarding this part.
Yes.
I tried sorting them by surface area, like in proportion to surface area, but that was wrong.
Yes,
like-
that will be wrong.
So when there was another case, another question where you had to do that. So I don't really get the difference.
Today itself, you mean to say?
No, sir. Like there was another question I remember where two spheres were brought in contact with like varying sizes but also varying charges.
Uh-huh.
So, and it was done with respect to surface area that time.
No. Okay, I understand what system you're talking about, but if you go back, you will see that
Yeah.
there also, we have, used, you would have used the equality of potential only to
Oh,
find the final charges. Okay.
yes. All right.
In fact, you would have realized that the surface charge density is going to be higher on the smaller sphere, and
Yes.
it will be lower on the larger sphere.
Yes.
Right. Okay. See, the reason for that is very simple, because we know that, as long as there is a potential difference, charges will continue to flow. Right. So that flow will only stop when the potentials become equal. So it is
Yes.
as simple as that. All right. Okay. Good. All right. Any other questions here?
So can we take the three? Can we take it as a system of capacitors and use the derivation where you do E dot ds? You take a unit charge and you move it from the center of the first sphere all the way up to the to infinity, and you see the change in energy. Will
Yeah,
that
you
work?
can. Yeah, you can do that, and it will work. Okay, but you can see that that will involve integration.
Yes, sir.
Right. Okay. And the electric field between the first and the second shell is going to be different than the electric field between the second and the third shell. So your integration will have two terms.
Three, right? From third shell to infinity also we have to take.
No. The idea is still to say that the potential, at both the surfaces is the same.
No, sir, I'm talking about the previous question. Sorry, the energy one.
Oh, the energy one. Okay. Right. For which one? Which term? U1 or U2?
Sir, instead of taking U1 and U2, can we
Ah.
do the energy stored in a what is that? Energy stored in a capacitor. We integrate the E dot something, E dot ds.
Okay. That will give you U1 term. If you try that, you'll get U1.
Yes.
Okay, and for interaction, I mean, still you have to calculate the interaction part separately.
Yes.
Okay, so this I think is the easiest way, to do it. Okay, but yes, what you're trying to say, will definitely it will work as well, right?
Yes.
But with more complex calculations.
Thank you, sir.
Yeah. All right. Any other questions here? Okay. So we still have time for one more question. Okay. Let's do. This is similar to the previous one. Okay, let us do this. This question I think is a good one. Okay, let's try this one. Okay, it's an electric field question, but it's a good question. Perhaps. Okay, if you have doubts understanding the geometry of the system itself, let me know.
So what does it mean for charges plus Q and minus Q to be distributed uniformly on the ring? Are they like what's the distribution?
In a sense, half the ring has a charge of plus Q, and the other half of the ring has a charge minus Q.
So the half is about the vertical diameter. That's what divides it.
Yes.
Yes.
Okay. So let us see how we can solve this. Here we are given a non-conducting ring. Okay, and it has a mass m and radius r. Okay, and there are charges of plus q and minus q. Okay, distributed uniformly on this ring. Okay, the ring is in a vertical xy plane. Right. So let us say that this is the ring. Okay, and this is the xy plane. Okay, which means z plane is normal to the screen. Okay, now we are putting this ring, okay, in a uniform electric field, okay, which is along the x direction. So we have a uniform field in that direction. Right. We want to find out what will be the time period of oscillation of this ring for a small rotation. Okay, so that's what we want. Fine. So first, let us try and think, how will the charge be distributed on the ring, right? We know that one half of the ring has negative and the other half has positive charge. Okay, now we have two options, right? One is, let us say I put the positive charge on the left half and the negative charge on the right half. Okay, and see what happens. Okay, so if I do that, positive here, negative here. Okay, and say this point is A here, and this point is B. Okay, so in this case, this is obviously the equilibrium position of the ring. Okay, now let us disturb it a little bit from this equilibrium position. Right, so let us say that I give it a little bit of rotation clockwise. Right, so what will happen? Okay, so if we rotate it a little bit clockwise, okay, point P will shift to the right and point A will shift to the left, right? So this is P dash and this is, or just P and A, right? These are the new positions of P and A. Okay, which means positive charge is over here and the negative charge is over here. All right, so now let us say that we draw a horizontal line like this. Okay, so the negative charge starts below this horizontal line. Basically, that's how I've drawn it. Okay, and in the same way, let us say we draw a horizontal line through point A. Right, so negative charge starts below it. Okay, now the reason I'm doing it is because I can see that if we do this, then the charge between the two horizontal lines, which is this charge and this charge. Okay, the forces will act on these two charges in such a way that the torque because of those forces will be 0. All right. Okay, so that is what we'll have. Okay, however, now above the top horizontal line, right, which is the charges in this portion. Over here, we can see that the force is going to be somewhat in this direction. Okay, and similarly for the charges in this portion of the ring, the force is going to be in this direction. Right, so you can see that this will create a clockwise torque. So if I disturb the ring, right, from its equilibrium position this way, okay, then it will continue to roll in the clockwise direction. Okay, it will not come back to its original position. It will not oscillate. All right. Okay, so that's not how we can put the charges, right? So we have to do the other way around. Okay, and hence the charges that we are going to put for oscillations to happen will be like this. Okay, point A here, B here. Right, so we have to put negative charge on this side and a positive charge on this side. Okay, because now if we disturb it, okay, a little bit from the equilibrium position, okay, so then the forces, once again, let's draw two horizontal lines. Okay, so same logic. Okay, no torque because of the forces between the two horizontal lines. Okay, so on this part of the ring, we can see that the force is going to be to the left And on this part of the ring, the force is going to be to the right. So now it has a tendency to come back. Okay. I have exaggerated over here, right? This theta is actually very, very small. Right. So in this case, let's try and find out what will be the time period of oscillation. Okay. So let us say that the charge over here, the negative charge is dq, right? And by symmetry, this charge is also going to be a dq, right? This is plus dq and that's minus dq. Okay. So the torque about O then will be equal to the value of the force. I can pick either F minus or F plus, either way. Okay, they are equal anyway, right? Into the distance between the two forces, right? It's a couple, so that's how we find the couple. Okay, F minus will be equal to dq into E into 2R. Okay, and dq we can find out, right, by saying that, okay, if this angle is theta, then this will be theta as well. Right, so dq will be equal to lambda, okay, into the length of that portion, which will be equal to, if r is the radius, then r into 2d theta, 2 theta rather. 2 theta. Okay, into E into 2r. Right, so when rearranging, the torque is 4 lambda r squared into E into theta. Yeah, okay, that's torque. Okay, and the torque we can write as I alpha. Okay, and I will just be about O, right? So it's a ring, so I'll just be mr squared. So alpha is equals to 4 lambda r squared E theta. Okay, so we lose the r squared from both sides, and alpha will be 4 lambda E by m into theta. Right, so then obviously this term over here is our omega squared. Okay, lambda is not really given to us in the system, so we can easily say that lambda is going to be equal to q by pi r. So I can put that here, okay, and solve for the time period. All right, this is how we can solve this. Okay, doubts here?
So I thought when they said like rotate about the vertical diameter, they're twisting it, like they're twisting the ring, so such that one half goes behind the plane and the other half comes in front of the plane.
Okay, that is a possibility as well, right? Okay,
So
I understand.
what is the answer given?
Yeah, if you follow these steps, okay, you will get the answer. Okay, so the answer is mentioned here, right? There is a pi missing in the answer. Okay, clearly we'll have pi over here, right? So that is missing, right? Okay. So apart from that, the you will get the answer that is given it. Okay, now let us see if there is something in the question that says about the rotation, small rotation about the vertical diameter. Okay. Yeah, we are not told whether the rotation is the way we have taken it, okay, or the way Vihan is saying, right? So I think what Vihan is saying here is that the rotation is given like this, okay, about the vertical axis like that. Okay, so for that rotation also, you can see that the ring is gonna be, is going to oscillate.
Yeah, so I got a very similar answer, like just the numerical values slightly different.
Right. I think this is also a fair way to look at it. Correct. All right. Okay, fine. Yes. Any other doubts here? Okay, so I think then that's pretty much it for today. Okay, I will stop here.
Thank you, sir. Bye, sir.
Thank you, sir.
Bye
Thank you
bye.
so
Thank
much.
you,
Sir.
sir.
Thank you,
Thank you,
sir.
sir.